Hello everyone, today I am here to explain the chapter Mechanism of Organic Reaction. Introduction. During a chemical reaction, reactant molecules are converted into product molecules. The arrangement of the atoms in the product molecules is altogether different from that present in the reactant molecules. This change, which is brought about the redistribution of electrons, usually occurs through some definite step. A detailed step-by-step description of a chemical reaction showing as to how reactants are converted into product is called reaction mechanism. In this unit, we shall study some important aspects of organic reaction mechanism. Arrow notation in organic reaction. Organic reactions usually involve making and breaking of covalent bonds. A covalent bond is often represented by a dash, and the movement of a pair of electrons is shown by a curved arrow. The movement of single electron on the other hand is shown by a fish arrow or half-headed arrow. For example, in the first ethane, we will we will move our electrons to the hydrogen positive and then its form two electrons it take one j then it will form CH2 positive and CH3, and in next there is a hydrolytic cleavage. In this notation, the tail of the arrowhead indicates the side from where the electron pair or single electron has to move, and head indicates to the side to which it has to move. In contrast, double-headed arrows do not indicate the movement of electrons but are used to separate various canonical structures. For example, benzene may be regarded as a resonance hybrid of two cuckyls, means first and second structure, and the three Dewar third to fifth structures. Now, next topic is types of bond fusion. Organic reaction occur through making and breaking of bond. There are two ways in which covalent bonds are broken. These are homolytic fission and heterolytic fission. Homolytic fissions, or we can also call it symmetrical fission. When a covalent bond joining two atoms A and B breaks in such a way that each atom of the covalent bond takes away one electron of the shared pair. It is called symmetrical cleavage or homolytic fission, or we can say homolysis, simply homolysis. The neutral chemical species such as A radical and B radical, which contain an odd or unpaired electron and which are produced by homolytic fission of covalent bond, are called free radical. Homolytic fissions usually occur in nonpolar bonds and is favored by high temperature or under the influence of UV rays and by the presence of radical initiators such as peroxide. Next is heterolytic or unsymmetrical fission. When a covalent bond joining two atoms A and B breaks in such a way that both the electrons of the covalent bond are taken away by one of the bonded atom. The mode of bond breaking is called unsymmetrical cleavage or heterolytic fission or simply heterolysis. Heterolytic fission is usually indicated by a curved arrow which denotes two electron displacement. As shown above, heterolytic fission results in the formation of ionic species, that is cations and anions. Further, heterolytic fission usually occurs in polar bond and is favored by polar solvents. Quite often the ionic species formed by heterolytic fission carry the positive or the negative charge on carbon atom. Such ionic species are called carbocation or carboanion respectively according to the carbon carries positive or negative charge. It may be emphasized here that the same covalent bond can undergo hemolytic or heterolytic fission under different conditions. In general, the bond dissociation energy for the homolytic fission are low while they are quite high for heterolytic fission. Reagents and the substrates. We know that whenever an organic reaction is carried out, we use certain starting materials called reactants. These are further classified as reagents and substrate. Actually, there is no clear cut distinction between these two terms because each one of them cannot react in the absence of the other. In general, a more a substrate may more precisely may be defined as a reactant which contain carbon atoms, some of whose bonds with other atoms are broken and some new ones are formed as a result of the reaction with the reagent. For example, in the reaction, ethylene will react with Br2 and it will form ethylene bromide. Ethylene is the substrate and the bromine is the reagent. Next is types of reagent. Reagents are broadly classified into two types: electrophilic reagents or electrophiles, nucleophilic reagents or nucleophiles. Electrophiles. Electrophile reagents or electrophiles are electron loving chemical species. Their lust for electron is due to the presence of an electron deficient atom in them. Electrophiles are of two types: positive electrophile and negative electrophiles. First is positive electrophiles. Electrophiles in which the electron deficient atom carries a positive charge are called electropositive electrophile. For example, proton, hydronium ion, bromium ion, chlorium, chlorium ion, carbonium ion, nitrium ion, benzene diazonium cation, aluminium ion, etc. Next is neutral electrophile. Electrophiles in which the atom deficient does not carry any charge are called neutral electrophiles. For example, free radicals, carbines, nitrines, borotetrafluoride, aluminium chloride, ferric chloride, stannic chloride, etc. In BF3, LaCl3, FeCl3, etc. The central atom has only 6 electrons in the valence shell and thus has a strong tendency to acquire a pair of electrons to complete its octet. However, in case of SnCl4, the central atom has the required octet of electron in the valence shell but still has a strong desire to accept more electrons because of the pair presence of vacant d orbital in it. Since both positively charged and neutral electrophiles are short by a pair of electrons, they have a strong tendency to seek electrons from other sources and thus they behave as Lewis acids. Due to their attraction for electrons, electrophiles always attack the substrate molecules at the site of highest electron density. Next is nucleophiles or nucleophilic reagents. Nucleophilic reagents are nucleus loving chemical species. Since the nucleus of any atom is positively charged, therefore, nucleophiles must be electron rich chemical species containing at least one unshared or lone pair of electrons. These are also of two types: negative nucleophile and neutral nucleophile. Negative nucleophiles which contain an unshared pair of electrons and are also negatively charged are called negative nucleophiles. For example, halides, hydroxide ion, alkoxide ion, amide ion, cyanide ion, carboanions, hydride ion, carboxylate ion, acetyl anion, etc. Next is neutral nucleophiles. Nucleophiles which contain an unshared pair of electrons but carry no charge are called neutral electrophile. For example, water, ammonia, amines, alcohols, ether, thioalcohols, hydroxylime, Grignard reagent, allyl or lithium aluminum hydride, sodium borohydride, etc. Since both neutral and negatively charged nucleophiles contain at least one lone pair of electron, they behave as a they have a strong tendency to donate this pair of electron to electron deficient atoms or species and hence behaves as Lewis acid. In other words, nucleophiles always attack the substrate molecule at the site of least electron density. Now there are some of the important characteristics of nucleophilic and electrophilic reagents are summarized below. Electrophiles. They are electron deficient species. Nucleophiles, electron rich species. Electrophiles accept and pair from the substrate. Next is acts as Lewis acid. Next is possesses an empty orbital to accept electrons from the substrate molecule, are either neutral or positively charged chemical species. Next characteristics of nucleophile reagents. They are electron-rich species. They donate an electron pair to the substrate, act as Lewis bases, are either neutral or negatively charged chemical species, possess at least one pair of electrons which can easily be donated to the substrate molecules. Next is type of organic reaction. All the organic reactions can be broadly classified into following types: substitution reaction, addition reaction, elimination reaction, condensation reactions, rearrangement reactions, isomerization, and the last one is paracyclic reaction. So let's discuss one by one. First is substitution reaction. A substitution reaction is that which involves the direct replacement of an atom or a group of atoms in an organic molecule by another atom or group of atoms without any change in the remaining part of the molecule. That is, the incoming group gets attached to the same carbon to which the outgoing group was attached. The product obtained as a result of substitution is called a substitution product, and the new atom or group of atoms which enters the molecule is called a substituent. Depending upon the nature of attacking spaces, the substitution reactions are of following three types. First is nucleophilic substitution reaction. Substitution reactions which are brought about by nucleophiles are called nucleophilic substitution reactions. In all these reactions, a stronger nucleophile usually displays a weaker nucleophile. These reactions are typical of alkyl halides. For example, hydrolysis of alkyl halide with an aqueous base to give an alcohol. Second is electrophilic substitution reaction. Substitution reactions which are brought about by the electrophiles are called electrophilic substitution reactions. In these reactions, the attacking species is an electrophile and the leaving group leaves without the pair of bonding electrons. These reactions are typical of arenes and other aromatic compounds where the high density of the electrons of the aromatic ring attracts the electrophiles. For example, halogenation, nitration, sulfonation, and Frieden-Crafts reactions. Now, third is free radical substitution reaction. Substitution reaction brought about by free radicals are called free radical substitution reaction. These are typical of alkanes and other saturated compounds. For example, chlorination of methane in the presence of heat or diffused sunlight to give methyl chloride and hydrogen chloride. These reactions occurs by a free radical mechanism which involves the first step. First is initiation, and this the chlorine bond is broken by homolytic fission in the presence of light, and we get the two radicals. Second, in the propagation step, we will take one methyl chloride radical plus one chloride, then it will form methyl radical and HCl is removed from this product. And last step we will do the termination, and then we will add the radical species and we will get the only product. Next is our addition reaction. Reactions which involve combination between the two reacting molecules to give a single molecule of the product are called addition reaction. Such reactions are typical of compounds containing multiple bonds, that is, double or triple bonds, depending upon the nature of the attacking species. Addition reactions are of following three types. First is nucleophilic addition reaction. Addition reactions brought by nucleophiles are called nucleophilic addition reaction. These reactions are typical of aldehyde and ketones. For example, base catalyzed addition of HCN to aldehydes or ketones. Next is electrophilic addition reaction. Addition reactions brought by electrophiles are called electrophilic addition reactions. These reactions are typical of alkenes and alkynes. For example, addition of Br2 or HBr to propine. Next is free radical addition reaction. Addition reactions brought about by free radicals are called free radical addition reaction. For example, addition of HBr to alkenes in the presence of peroxide. Now our next reaction is of elimination reaction. Elimination reaction is one that involves the loss of two atoms or group of atoms from the same or adjacent atom of a substance, leading to the formation of multiple bonds, depending upon the relative position of the atoms or group eliminated. These reactions are classified as alpha, beta, and gamma elimination reaction. Alpha elimination reaction. In this reaction, the loss of two atoms or group occurs from the same atom of the substrate molecule. For example, base catalyzed dehydrohalogenation of chloroform to form trichlorocarbene. Dichlorocarbon is the reactive intermediates involved in the carbon-lime reaction in the Remer-Timmer reaction. Next is beta elimination reaction. In this reaction, the loss of two atoms or group occurs from adjacent atoms of the substrate molecule. For example, acid catalyzed dehydration of alcohol and base catalyzed dehydrohalogenation of alkyl halides. Our next one is gamma elimination. In this reaction, loss of two atoms or group occurs from alpha and beta position, that is 3 bonds away of the molecules, leading to the formation of three-membered ring. This reaction is called the Froude reaction and is extensively used for the synthesis of three-member. The reaction is when 1,3-bromopropane is react in the presence of zinc zinc rust, it will form chloropropane and zinc bromide is removed from the product. Next, our fourth reaction is condensation reaction. In this reaction, two or more molecules of the same or different reactants combine to form a product with or without the elimination of simple molecules such as water, HCl, NH3, ROH, etc. For example, when two molecules of acetaldehyde condense in the presence of dilute alkali to form 3-hydroxybutanol, since beta hydroxyaldehydes or ketones are commonly known as aldols, therefore this reaction is also known as aldol condensation. Aldols on heating with dilute mineral acid radially undergo dehydration to form alpha beta unsaturated aldehydes or ketone. Just take an example, when 3-hydroxybutanol is treated with dilute mineral acid, it will form butane to enol, and the side product is water, and this is called croton aldehyde. Our next reaction is rearrangement reaction. Reaction involving the migration of an atom or a group from one atom to another within the same molecule are called rearrangement reaction. For example, first is deaddition of 3-methyl butane to all with concentrated H2SO4 occurs through 1,2 migration of hydride ion to give the rearranged product, that is 2-methyl butane. However, when 2,2-dimethylpropane is treated with concentrated H2SO4, it involves migration of 1,2 of the methyl group to give the same rearranged product, that is 2-methyl-butane. Next is Hofmann bromide reaction involving the conversion of primary amides to primary amines on the treatment with Br2 in the presence of KOH. In this rearrangement reaction, the group R migrates from carbon to nitrogen to first give an alkyl isocyanate, which upon hydrolysis give an primary amine with one carbon atom less than the original amide. Our sixth reaction is isomerization reaction. Reactions which involve interconversion of one isomer into another, keeping the molecular formula as well as the carbon skeleton of the reactant and the products intact, are called isomerization reaction. For example, interconversion of trans-butadiene to cis-butadiene and vice versa may be regarded as geometrical isomerization reaction. Next is paracyclic reaction. There are a large number of organic reactions which do not involve ionic or free radical intermediates. Instead, these reactions occur in a single step via a cyclic transition state. In these reactions, bond making and bond breaking occur simultaneously. These reactions do not require any catalyst and are initiated either by heat or light. All such reactions are called paracyclic reaction. For example, electrocycline and cycloaddition reaction. First is electrocyclic, involves conversion of acyclic conjugated dienes to cyclic alkanes and vice versa. In cycloaddition, the addition of diene to a dienophile to form a six-membered ring is called Diels-Alder reaction. These are the different types of reaction. Now our next topic is energy consideration. The ultimate criteria for the feasibility of any chemical reaction is given by Gibbs free energy, that is delta G, which is related to the enthalpy delta H and entropy change delta S by the reaction. And the expression is given by delta G is equal to delta H minus T delta S. It should be noted that the reaction proceeds in the forward direction only when the delta G is negative, that is, gives free energy is negative. A positive delta G, on the other hand, suggests that the reaction has a tendency to proceed in the backward direction. Further, since entropy is a measure of the degree of randomness of a system, therefore, system is most stable when it has maximum entropy. On the other hand, reaction in which there is a loss of randomness should not be favorable, and it has ended been found that reaction involving a decrease in the number of molecular species and going from reactants to product proceed only if delta H is negative. That means the reaction is of exothermic and also large enough to make delta G negative. Conversely, when the number of the molecule space is increasing in going from reactant to product, there is an increase in the entropy of the system, and minus T delta S term becomes less large enough to make the reaction move in the forward direction even when it is not an exothermic reaction. When the substances are taken in the standard state, that means the temperature is 273 Kelvin and the pressure is 1 atmospheric. The above the above expression may be written as delta G naught is equals to delta T T naught minus T delta S naught, where subscript 0 is used to denote standard states and delta G naught is the difference in the standard free energies of the product and the reactant. However, in the case of equilibrium reactants, the equilibrium constant K is related to delta G naught by the following expression. That means delta G naught is equals to minus RT ln K. It may be noted that K denotes the extent of a chemical reaction. A high value of K indicates that the reaction proceeds significantly in the forward direction. Next is collision theory. A chemical reaction is believed to take place through collision between the reactant molecules. The number of collisions that take place per second per unit volume of the reaction mixture is called collision frequency. At ordinary temperature and pressure, the value of collision frequency is so high in the gaseous reaction that if all the conditions were effective, that is, result in the formation of the product, the reaction should be completed within a fraction of second. However, in actual practice, this is not so because most of the chemical reactions are slow and many of them do not take place even at room temperature. This may be explained as follows. First is energy factor. For a collision to be effective, the colliding molecules must have a certain minimum amount of energy called threshold energy. Since at ordinary temperature and pressure, most of the reactant molecules do not have energy equal to the threshold energy in the ground state. They have to be supplied some extra energy so that their collisions become more effective. This minimum amount of extra energy which must be supplied to the reactant molecule in the ground state so that their energy becomes equal to the threshold energy is called the activation energy. Activation energy is equals to threshold energy minus energy of the reactant and the ground state. Evidently, lesser is the activation energy, faster is the reaction, or greater the activation energy, slower is the reaction. Next important factor is orientation factor or the possibility factor. In some cases, it is found that even if a large number of colliding molecules have more energy than threshold energy, still the reaction is slow. This is due to the reason that at the time of collision, the reactant molecules do not have the proper orientation for reaction to occur. This is called orientation factor or the probability factor. Thus, from the above discussion, it follows that rate is equals to collision frequency multiply energy factor into probability factor. That implies R is equals to PZ into e की power E activation divided by RT, where Z is the collision frequency, P is the probability factor, E act is the energy of activation, and E minus EA activation divided by RT is the friction of collision with energy greater than activation energy. Next is transition state theory. Transition state theory has been found to be more useful and understanding the mechanism of organic reaction. According to this theory, collision between the reactants lead to the formation of highly energy spaces called the activation complex or the transition state. This species lies at the top of the energy barrier, separating the reactant and the product. The activation complex is substituting decomposes to give the product. In other words, reactant on their way to product pass through a transition state. This sequence of events are shown in energy profile diagram, a one-step diagram that is in figure one-step reaction in figure 2.1. The rate of the reaction depends upon the rate at which the reactants are converted into the transition state rather than on collision frequency as was postulated in the collision theory. Since the transition state is in equilibrium with the reactant and there is its n, hence its concentration is determined by equilibrium constant K, which is related to the free energy of the activation by the reaction. Delta G positive is equals to delta H positive minus T delta S positive is equals to minus 2.303 RT log K, where delta H positive is the enthalpy of activation and S positive is the entropy of activation. The activated complex or the transition state, that is A, B, C, is not a true molecule since it contains partial bonds and the energy of the system is maximum. Its life is extremely short and hence it cannot be isolated. It finally decomposes to give the products A, B, and C shown in the figure 2.1. The free energy of the activation of the reaction, besides other factors, depends upon the strength of the BC and AB bond. The stronger the BC bond, higher is the energy of activation, and conversely, stronger is the AB bond, lower is the activation energy. Further, since the free energy of activation represents the energy barrier, it affects the rate of the reaction. Higher the energy barrier, slower is the reaction, and conversely, lower the energy barrier, faster is the reaction. In contrast, delta G naught is a thermodynamic quantity. It merely gives the difference in standard free energy of the reactants and the products, and hence does not affect the rate of the reaction. We have discussed above energy profile diagram for one step reaction, but many organic reactions occur in two steps. In all such reactions, the initially formed transition state first decomposes into a relatively less energetic but more stable species than the activated complex. These chemical species, which is less energetic but more stable than the activated complex, is called the reactive intermediate. This reactive intermediate finally gets converted into the product through another activated complex or the transition state that will be shown in figure 2.2a and 2.2b. Thus, a two-step reaction occurs through two transition states. If the free energy of the activation of the first transition state is higher than that of the second in figure 2.2a, then the intermediate readily get converted into the product. That is, the intermediate cannot be isolated. In such cases, the first step is called the redetermining step of the reaction. If, however, the free energy of the activation of the second transition state is higher than that of the first, as shown in the figure 2.2b, then the intermediate is quite stable and hence can be isolated. In such cases, the second step is called the redetermining step of the reaction. In the light of the above discussion, a reaction may follow the following steps. First, pathway substrate plus reagent is equals to transition state, and that is equals to the product. Path 2, substrate plus reagent is equals to transition state 1, that after it will form intermediate, and again transition state 2, and then finally we will get the product. A detailed step-by-step description of chemical reaction showing as to how reactants are converted into products is called the mechanism of the reaction. If a reaction involves simultaneously making and breaking of bonds without the formation of any intermediate, it is said to be concentrated reaction. Such a reaction occurs through a single transition state that is shown in the figure 2.1. On the other hand, if a reaction occurs in two or more steps with the formation of reactive or Isolabel intermediate. It is said to be stepwise or non-concentrated reaction that is shown in the figure 2.2a and 2.2b. The number of transition states formed during a stepwise reaction is equal to the number of steps by which the reaction occurs. Thus, a two-step reaction has two transition states, of which the one having higher free energy of activation constitutes the rate determining step of the reaction. Our next topic is reactive intermediate. Most of the reaction occur through a participation of certain chemical species with generally short-lived and highly reactive. Therefore, these species cannot be isolated. Their involvement can only be detected either by spectroscopic method or by tapping them with more effective substrate. These short-lived, highly reactive chemical species are called reaction intermediates or reactive intermediates. Some important examples of the reactive intermediates are carbocations, carboanions, free radicals, carbenes, nitrogens, arynes, and enamines. Now let's discuss one by one. Now first is carbocation. Chemical species carrying positive charge on a carbon which has only 6 electrons in its valence shell are called carbocations or carbonium ions. Carbocations are short-lived, highly reactive chemical species. Since the carbon atom carrying the positive charge is electron deficient, that means it has only 6 electrons, and thus has a strong tendency to complete its octet by accepting a pair of electrons. Now next is generation of the carbocations. Carbocations are produced by heterolytic cleavage of a covalent bond in which the leaving group takes away both the bonding electrons of the covalent bond. Some of the reactants in which carbocations are formed are summarized below. First, in the ionization of the alkyl halides. Second, by the protonation of unsaturated compounds such as alkenes, carbonyls, carbonyl compounds, and nitriles. थर्ड बाय प्रोटोनेशन ऑफ एल्कोहल्स फॉलोड बाय डिहाइड्रेशन. इसके अंदर हम एल्कोहल लेंगे, उसको एच पॉजिटिव देंगे, देन इट विल फॉर्म आर ओ एच पॉजिटिव आर ओ एच टू पॉजिटिव. देन इन नेक्स्ट स्टेप वी विल गेट carbonium ion and the vote will be as a side product. By deamination of primary aliphatic amines with nitrous acid. Now last step is by action of superacid on alkyl fluorides. Next is classification. Carbocations are classified as primary, secondary, or tertiary according as the carbon carrying the positive charge is primary, secondary, or tertiary in nature. Methyl carbocation having only one carbon, however, regarded as a special case. If the carbon is attached to only one carbon and carrying a positive charge is called primary carbocation. If a carbon is further directly attached to two carbon atoms and carrying positive charge is called secondary carbocation. Similarly, if the carbon is attached to three groups and to which the groups are attached are of positive charge, then it is called tertiary carbocation. Orbital structure. The carbocations are planar chemical species. The carbon atom carrying the positive charge is sp2 hybridized. The three sp2 hybridized orbitals of this carbon form three sigma bonds with three monovalent atoms or group which lie in a plane and are inclined to one another at an angle of 120 degrees. The unhybridized 2p orbital, which is perpendicular to the plane of the three orbitals, is, however, empty, that is shown in the figure 2.4. Stability. Stability of carbocation can be explained on the basis of laws of electrostatics, which state that any factor which tends to disperse the positive charge by distributing it over test of the molecules must stabilize the carbocation, while any factor which tends to intensify the positive charge must destabilize the carbocation. Ability of alkyl carbocation. The order of stability of simple alkyl carbocations follow the order. Secondary is more reactive than primary. The order of stability can be explained on the following basis. First is inductive effect. We know that alkyl groups have electron donating inductive effect, that is plus I effect. Because of their plus I effect, they release electrons towards a positively charged carbon, thereby Dispersing the positive charge. The dispersal of the charge leads to the stabilization of the carbocation. Evidently, greater the number of such alkyl groups attached to the positively charged carbon, greater will be the dispersion of the positive charge, and hence more will be the stability of the carbocation. Thus, a tertiary carbocation will with the three alkyl groups should be more stable than secondary carbocation with two alkyl groups, which in turn should be more stable than a primary carbocation with one alkyl group, while methyl carbocation with no alkyl group will however will be the less stable. So the order is tertiary and then secondary and then primary, and the last one is methyl carbocation. Second, on the basis of hyperconjugation. The stability of carbocations can also be explained on the basis of hyperconjugation. In general, greater the number of alpha hydrogens, greater is the number of hyperconjugated structure, and hence more stable is the carbocation. Thus, tertiary butyl carbocation with 9 alpha hydrogens and hence 9 hyperconjugation structure is more stable than isopropyl carbocation with the 6 alpha hydrogens and 6 hyperconjugated structures, which in turn is more stable than ethyl carbocation with 3 hydrogens and 3 hyperconjugated structures, while methyl carbocation with no alpha hydrogen has no hyperconjugated structure is the least stable. Thus, the order of stability of alkyl carbocations follow the sequence: third butyl, then isopropyl, then ethyl, and then the methyl carbocation. Steric effects. As discussed above, carbocations are planar chemical species, but most of the compounds from which they are obtained have tetrahedral structure. Thus, in the formation of carbocations, bond angle between the two groups decreases from 109 degree 28 inches to 120. In other words, the group move apart. This moving away of the group relieves some of the steric strains present in the starting compounds. Evidently, greater is the relief in the steric strain, more easily a carbocation is formed. Since the extent of steric relief is expected to be maximum in the formation of tertiary carbocation is followed by secondary and primary carbocations and least in the case of methyl carbocation. Therefore, the order of stability of various carbocation follows the sequence in the decreasing order, that is the tertiary, secondary, primary, and the last one is methyl. Second, second we can also explain the stability of unsaturated carbocations. Stability of carbocations in which the positively charged atom is next to double bond or benzene can be best explained on the basis of resonance effect. For example, consider the following step cases. First, stability of allyl and benzyl carbocations. Allyl and benzyl carbocations are stable through the dispersal of the positive charge through a resonance. Now we will see the resonance stabilization of allyl carbocation and benzyl carbocation. Evidently, larger is the number of phenyl group attached to the carbon atom which is bearing the positive charge. Greater is the delocalization of the electron or dispersal of positive charge, and more is the stability of the carbocation. Thus, diphenyl methyl carbocation is more stable than benzyl carbocation due to the greater number of resonating structures. Similarly, triphenyl methyl carbocation is still more stable than diphenyl methyl carbocation due to the still larger number of of resonating structure. Triphenyl carbocation is so stable that its salts such as perchlorates, fluoroborates, etc. can be isolated and stored indefinitely. Thus, the overall stability of benzyl, diphenyl, methyl, and triphenyl methyl carbocations follows the order. Triphenyl methyl is more reactive than diphenyl methyl carbocation, and diphenyl methyl is more reactive than benzyl carbocation. Similarly, triphenyl cyclopropenyl carbocation is more stable than diphenyl cyclopropenyl carbocation, which in turn is more stable than phenyl cyclopropyne carbocation. Next is effect of substitution on the stability of the benzyl carbocations. Presence of electron donating group such as R, OH, OR, NH2, NH, R, N2, etc. at ortho para positions tends to stabilize the substituted benzyl carbocation relative to benzyl carbocation by dispersal of positive charge due to the Pulsar effect. of the substituent. Conversely, presence of electron withdrawing groups such as CN, NO2, CHO, COR, CWH, COR at ortho para position tends to destabilize the substituted benzyl carbocation related to the benzyl carbocation by intensification of positive charge due to minus side effect of the substituent. Thus, paramethoxybenzyl carbocation is more stable than benzyl carbocation, and further benzyl carbocation is more stable than para-nitrobenzyl carbocation. Second is stability of tropylium ion or cycloheptarenyl cation. Tropylium cation is usually unstable. This unusual stability is due to the reason that it is an aromatic cation containing 6 pi electrons, that is 2 electrons from each of the 3 double bonds. These 6 electrons are completely delocalized over the 7sp2 hybridized carbon atom as shown below, just in the same manner as, as the 6 electrons are destabilized delocalized in benzene ring. Actually, the tropylium ion is so stable that its reaction with nucleophiles such as water, alcohols, etc. is very small. Second, the instability of cyclopentadienyl cation. Like cycloheptatrienyl cation, cyclopentadienyl cation should also be stabilized by resonance since the carbon atom carrying the positive charge is conjugated with two double bonds. Actually, this carbocation is highly unstable, and the reason for this instability is that it is an anti-aromatic cation containing 4 pi electrons. The instability of anti-aromatic compounds can be explained on the basis of HMO diagram, which we will learn in semester second. Stability of alkoxy-alkyl carbocations. Carbocations in which the carbon atom bearing the positive charge is attached to the heteroatom such as oxygens, nitrogens, halogens, etc. are also stabilized by resonance. Because of the resonance stabilization, methoxymethyl can be isolated as stable solid. Next is stability of acyl cations. Like alkoxy-alkyl cations, acyl cations are also stabilized by resonance. Although, due to the presence of a positive charge on the more electronegative oxygen atom, the contribution of canonical structure second is far less than the structure first to the resonance hybrid. Yet, acetyl cation CH through two positives almost as stable as third butyl carbocation. Instability of vinyl and phenyl carbocation. Carbocations in which the positive charge is located on the doubly bonded carbon atoms such as vinyl and phenyl cations cannot be stabilized by the resonance since the sp2 orbital of the carbon atom carrying the positive charge is perpendicular to the p orbitals of the double bond. As such, these are very short-lived chemical species. However, vinyl cations are more stable than methyl carbocation but less stable than even primary carbocation as discussed below. The relative stability of the carbocations can be easily measured through heterolytic bond dissociation energy. The lower is the heterolytic bond dissociation energy, greater is the stability of the carbocation. The second is carboanions. Chemical species carrying a negative charge on the carbon are called carboanions. In this species, the carbon atom carrying the negative charge has 8 electrons in the valence shell, 6 from 3 covalent bonds and 2 from the lone pair of electrons. The carboanions, like carbocations, are also short-lived, highly reactive chemical species even though the carbon atom carrying the negative charge has an octet of electrons. The instability of carboanions is believed to be due to the presence of formal charge on them. Generation of the carbanions. Carbanions are produced by heterolytic cleavage of a covalent bond in which the leaving group departs without the bonding electrons of the covalent bond. This implies that every carboanion has one lone pair of electrons which it can donate. Therefore, carboanions may be regarded as Lewis base or nucleophiles. These are usually generated by the following method. First is by the abstraction of the hydrogen from the carbon atom alpha to nitrous, cyano or carbonyl groups with a strong base. Second is by the abstraction of hydrogens of terminal acetylenes with a strong base. And the third is by the addition of nucleophiles to alpha beta unsaturated compounds. Classification of carboanions. Carboanions are classified as primary, secondary, or tertiary according to the carbon which carrying the negative charge is primary, secondary, or tertiary in nature. Methyl carbocation containing one carbon is, however, regarded as a special case. Methyl carboanion containing only one carbon is, however, regarded as a special case. Next is orbital structures of carboanion. The structure of simple allyl carboanions is usually pyramidal, just like that of ammonia. The carbon carrying the negative charge is sp3 hybridized. Three of the four sp3 hybridized orbitals from three bonds with monovalent atoms or group, while the fourth sp3 orbital contains the lone pair of electrons that will be shown in the figure 2.5. Since the lone pair bond pair repulsion are expected to be greater than the bond pair repulsion, the bond angles in carboanion are much lesser than the regular tetrahedral angle of 109 degree 28 inch. In other words, carboanions do not have the regular tetrahedral geometry, but they have pyramidal structures in which the bond angles are in the between 97 to 100 degrees. As a result, carbanions can also have planar geometry. It has been discussed above that the shape of the simple alkyl carbanion is pyramidal. However, when the lone pair of electrons on the carbon atom carrying negative charge is conjugated with the multiple bonds, then the carbanions are always planar. This is due to the reason that these carbanions are stabilized by resonance and for an on for resonance to occur. It is essential that the lone pair of electrons must be in p orbital so that it can overlap with the p orbitals of the pi bond that will be shown in the figure 2.7. Thus, in alternate planar structure, the carbon atom carrying the negative charge is sp2 hybridized. Some other examples of planar carbanions are benzyl carbanion, diphenyl methyl carbanion, triphenyl methyl carbanion, and other carbanions obtained by the abstraction of alpha hydrogen atom from a carbonyl compound. Next is we will discuss the stability. Like carbocations, stability of the carbanions can be easily explained on the basis of inductive and resonance effects. First is inductive. The stability of simple carbanions follows the sequence methyl, then methyl is more reactive than primary, and primary is more reactive than secondary and by tertiary. This order of stability is exactly reverse of that of the carbocations and the free radicals and can be easily explained on the basis of inductive effect as discussed below. Due to the electron releasing inductive effect plus I effect of the alkyl group, the intensity of density of the negative electron on the central metal atom increases. This intensification of the negative charge leads to the instability of the carbanion. Evidently, greater the number of alkyl group attached to the carbon atom, which is bearing the negative charge, greater will be the intensification of the negative charge, and hence more stable will be the carbanion. Thus, the methyl carbanion with no alkyl group should be the most stable, followed by ethyl carbanion with one methyl group and isopropyl carbanion with two methyl groups, while tertiary butyl carbanion with three methyl groups should be of least stable. Type of hybridization. The relative stability of the carbanions derived from alkenes, and alkanes can be explained on the basis of type of hybridization carrying of the carbon carrying the negative charge. For example, in acetylene anion, align the S character hybridization is sp and S character is 50. Further, in the ethylene carbanion, the hybridization is sp2 and S character is 33, and in the ethane carbanion, the hybridization is sp3 and S character is 25. As the S character of the carbon carrying the negative charge increases, the stability of the carbanion increases since the electrons are closer to the nucleus and hence of lower energy. Next is resonance effect. Carbonyls in which the unshared pair of electrons are present on the negatively charged carbon is attached to the multiple bonds or a phenyl group are much stable than simple alkyl carboanions. This is due to the reason that these carboanions are stabilized by resonance. First is stability of allyl and benzene carboanions. Allyl and benzene carbanions are stabilized by the dispersal of negative charge through resonance. Evidently, larger the number of phenyl groups attached to the carbon atom bearing the negative charge, greater is the delocalization of the electrons or the dispersal of negative charge, and more stable is the carbanion. Thus, diphenyl carbanion is evidently larger the number of phenyl group attached to the carbon atom bearing the negative charge, greater is the delocalization of the electrons or dispersal of negative charge, and hence more stable is the carbanion. Thus, diphenyl carbocation is more stable than benzyl carbocation due to the greater number of resonating structures. Trimethyl carbanion is still more stable than diphenyl methyl carbanion due to the still larger number of resonating structures. Next is effect of substituents on the stability of benzyl carbanions. Presence of electron donating groups such as R, OH, NH2, etc. at ortho para positions of the phenyl group with respect to the carbon bearing the negative charge tends to destabilize the substituted benzyl carbanion relative to the benzyl carbanion by intensification of the negative charge due to pulsar effect of the substituent. Conversely, presence of electron withdrawing groups such as Cn negative, NO2 negative, CHO, COR, COH, COR negative, etc. at ortho pair positions tends to stabilize the substituted benzyl carboanion relatively to the benzyl carboanion by the dispersal of negative charge due to the minus R effect of the substituent. Thus, nitrobenzyl carbanion is more stable than benzyl carbanion, and further benzyl carbanion is more stable than paramethoxybenzyl carbanion. Next is stability of cyclopentadienyl anion. Cyclopentadienyl anion is sorry, unusually stable since it is an aromatic anion containing 6 pi electrons. The 6 pi electrons are completely delocalized on all the 5 sp2 hybridized carbon atoms as shown below, just in the same way as the 6 electrons of the benzene are completely delocalized over the 6 sp2 hybridized carbon atoms of the benzene ring. This dispersal of negative charge accounts for the unusual stability. Consequently, it has a high resonance energy as compared to of benzene, and hence cyclopentadiene and atom is quite stable. Next is the stability of carbanions carrying electron withdrawing group. Electron withdrawing groups such as ketone, carboxylic acid, carboxylate, NO2, CN, etc. tends to disperse a negative charge by resonance and hence increases the stability of the carbanions. Next is free radical. Chemical species carrying an odd or unpaired electrons are called free radicals. That, for example, required methyl free radicals, methyl free radical, phenyl free radicals, formula is C6H5 radical, C6H5 dot C, sorry, radical CH2, that is called benzyl free radical. 6H5 3 carbon dot is called, that is called triphenyl methyl free radical. Although free radicals are themselves electrically neutral, yet due to the presence of an odd electron, they are weakly attracted by the magnetic field and hence they are paramagnetic in nature. Like carbo and cations and anions, free radicals are also short-lived in highly reactive chemical species because of their tendency to acquire one more electron to complete the octet. Further, because of their tendency to acquire one more electron, free radicals may also be regarded as electrophiles. Next is called the classification of free radicals. Free radicals like carbocations and carboanions are classified as primary, secondary, and tertiary according as the carbon atom carrying the unpaired electron is primary, secondary, or tertiary in nature. Orbital structure. The alkyl free radical are planar chemical species. The carbon atom carrying the odd electrons is sp2 hybridized. The three sp2 hybridized orbitals of this carbon form three bonds with monovalent, three sigma bonds with monovalent atoms or groups which lie in a plane are inclined to one another at an angle of 120 degrees. The unhybridized 2p orbital, which is perpendicular to the plane of these three sigma bonds, however, contains the odd electron, which is shown in the figure 2.8. Stability. Like carbocations, the stability of free radicals can also be easily explained on the basis of hyperconjugation and resonance effect as discussed below. Hyperconjugation effect. Like carbocations, the stability of simple alkyl free radicals follows the sequence tertiary, then secondary, then primary, and then methyl. The order of stability can be explained on the basis of hyperconjugation effect. In general, greater the number of hyper alpha hydrogen, greater is the number of hyperconjugated structure and hence more is the stability of the free radical. Hence third butyl free radical with 9 alpha hydrogens and hence 9 hyperconjugation structure is more stable than isopropyl free radical which has 6 alpha hydrogens and 6 hyperconjugation structures, which in turn is more stable than ethyl free radical with 3 alpha hydrogens and hence 3 hyperconjugation structure, while methyl free radical with no alpha hydrogen has no hyperconjugated structure as the least stable. Second effect is resonance effect. Free radicals which are stabilized by resonance are even more stable than simple alkyl free radical. For example, allyl and benzyl free radicals are stabilized by resonance through delocalization of unpaired electrons over the bond or the benzene ring. Evidently, larger the number of phenyl groups attached to the carbon atom carrying the unpaired electron, greater is the delocalization of the electrons, and hence more is the stability of the free radical. Thus, diphenyl methyl free radical is more stable than benzyl free radical due to the greater number of resonating structures. Similarly, triphenyl methyl free radical is still more stable due to the large number of resonating structures. Radicals in which the odd electron is located on a doubly bonded carbon atom such as vinyl or phenyl radical cannot be stabilized either by hyperconjugation or by resonance and hence are usually very short-lived. These radicals are even less stable than methyl-free radicals. Let's proceed further, that is carbenes. First we will give its definition. Neutral divalent carbon species in which a carbon atom is bonded to two monovalent atoms or grouped by covalent bond and has two non-bonding orbitals containing two electrons between them are called carbenes, and these are also called methylene. However, in actual practice, the parent species, that is uh, CH2 is called double dot CH2 is called methylene, but its derivative are commonly called carbenes. Like carbocations, carbenes are also short-lived, highly reactive chemical species since the central atom has only 6 electrons in the valence shell and thus has a strong tendency to complete its octet by gaining 2 more electrons. This carbenes behaves as Lewis acid or electrophiles. Typical reactions which involve carbon intermediates are carbylamine reaction and Rimer-Tiemer reaction. Next is generation of the carbenes. They are generated by the following two methods: by thermal or photochemical decomposition of cyclopropanes and oxiranes, and second step by thermal and photochemical decomposition of diazoalkanes or ketones. Third is by the action of strong base, usually potassium tert-butoxide on chlorophyll. This reaction is an example of alpha elimination since H and Cl are lost from the same carbon atom. Types of carbenes. Depending upon the distribution of two non-bonding electrons between two orbitals, the carbene are of following two types: singlet carbon, and second one is triplet carbons. If two non-bonding electrons are present in one orbital and the other orbital is empty, the carbon is said to be singlet, and a singlet carbon such as singlet methylene is usually represented by one arrow is above and one arrow is below CH2. Since a singlet carbon has no unpaired electron, it has no dipole moment and hence it is diamagnetic. Being diamagnetic, it cannot be detected by electron spin resonance, that is ESR spectroscopy. Further, on the next hand, if the two non-bonding electrons are unpaired and are present in two different orbitals of equal energy with their spin parallel in accordance with Hund's rule, the carbon is said to be triplet carbon. The triplet carbon, such as triplet methylene, is usually represented by two arrows with headed above. Unlike singlet carbene, a triplet carbon has a permanent dipole moment. Further, since a triplet carbon has two unpaired electrons, hence it is paramagnetic, hence can be easily detected by ESR spectroscopy. Orbital structure. In the singlet carbon, the central carbon atom is sp2 hybridized. That means two of the sp2 hybridized orbitals are used in the forming of two sigma bonds with two monovalent atoms or groups, while the third sp2 orbital contains the two non-bonding electrons. The unhybridized p orbital is however empty, that is will be shown in the figure 2.9. Thus the singlet carbon is a bent chemical species. The structure of the singlet carbon is similar to that of the carbocation, since in both of them carbon is sp2 hybridized and 1p is empty. In triplet carbene, the central atom is sp hybridized. Two of the sp orbital form two sigma bonds with two monovalent atoms or group, while the two unhybridized p orbital, that is py and pz, are perpendicular to each other and contain one electron each, which is shown in the figure 2.9. Thus, a triplet carbon is a linear species and behaves like a diradical or biradical. Now we will discuss the stability. A triplet carbon is always more stable than the corresponding singlet carbon. This is due to the reason that in singlet carbon, the two non-bonding electrons are present in the same orbital and thus tend to repel each other. This interelectronic repulsion increases the energy of the singlet state relative to the triplet state, in which the two non-bonding electrons are present in different orbitals. This is supported by the observation that triplet methylene is about 35.5 kJ per mole more stable than the singlet methylene. Further, carbons in which the central atom is attached to two atoms, each one of which has a lone pair of electrons, are somewhat more stable than methylene due to the resonance. Our next intermediate is nitrines. Nitrines are the nitrogen analogues of carbons. These are defined as neutral monovalent nitrogen species in which nitrogen has two unshared pair of electrons and is bonded to only one monovalent atom or a group. Like carbons, nitrines are also short-lived, highly reactive chemical species since the nitrogen has only a subset of electrons in the valence shell and thus has a strong tendency to complete its octet by gaining two electrons. Thus, nitrines like carbons behaves as Lewis acid or electrophiles. A well-known reaction which involves nitrine intermediate is Hofmann bromide reaction, which brings about the conversion of primary amides to primary amines containing one carbon atom less than the original amide. Next is generation of nitrines. These are generated by the following methods. First is by thermal photochemical decomposition of azides or isocyanates. Second is by base catalyzed elimination of sulfonate ion from orthohydroxylene or sulfanotes. Types of nitrines. Like carbons, nitrines are also of two types, singlet and triplet. In singlet nitrines, the four non-bonding electrons on nitrogen are present in two pairs, but in triplet, these are present in the form of one pair and two unpaired electrons. For Better understanding, see figure 2.10. Orbital structure. In the singlet nitrogen, the nitrogen atom is sp2 hybridized. One of the sp2 hybridized orbital form a sigma bond with a monovalent atom or group, while the other two sp2 orbitals contain a pair of electron each. The unhybridized p orbital is however empty. In triplet nitrene, the nitrogen atom is sp hybridized. That is, one sp orbital form one sigma bond with a monovalent atom or a group, while the other contains a pair of electrons. The two unhybridized p orbital py and pz are perpendicular to each other and contain one electron each. See figure 2.10. Stability and detection. Nitrines are too reactive to be isolated under ordinary conditions. Alkyl nitrines have been isolated by trapping the matrices at 4 Kelvin, while aryl nitrines, being less reactive, can be trapped at 77 Kelvin. The trapping of the nitrines is usually carried out by its reaction with carbon monoxide to yield isocyanides. Next is arynes. Aromatic compounds containing a formal carbon triple bond are called arynes. The best known aryne is benzene, which is the aromatic analog of acetylene. In other words, it may be regarded as benzene minus with two ortho hydrogens and hence can be called as dihydrobenzene. Structure. The triple bond of the benzene is altogether different from that of acetylene. In acetylene, it is made up of two sp sigma bond and two pi bonds formed by sideways overlapping of p orbital. However, in benzene, the triple bond consists of one sp2 sigma bond and two pi bonds. One of the pi bond is formed by the sideways overlapping of the two orbitals, while the other is obtained by sideways overlapping of two sp2 orbitals as shown in the figure 2.11. This new pi bond lies along the side of the ring and hence has little interaction with the pi electrons cloud lying above and below the aromatic ring. Since the sideways overlapping of sp2 orbital is not good, therefore the new pi bond is very weak and hence benzene is highly reactive molecule. Generation and the detection of the arynes. By action of soda lime and liquid ammonia on aryl halides, benzene has been shown to be the intermediate in nucleophilic substitution reactions of aryl halides. For example, in the presence of a strong base, aryl halides eliminate a molecule of HX from ortho positions to form arynes, which subsequently readily react with the available nucleophiles to form the substitution product. This mechanism is called either benzene mechanism or the elimination addition reaction. Similarly, the intermediacy of benzene and the Dove's method for industrial production of the phenol from chlorobenzene and strong alkali has been demonstrated by 1 to 14 carbon benzene. Second step, by the thermal decomposition of benzene diazonium to carboxylate. For next is detection. Arynes are usually detected either through mass spectroscopy or by chemical reactions such as dimerization or cycloaddition reaction with substances like furan. The most two important reactions of arynes are nucleophilic addition and cycloaddition. First is nucleophilic addition and the cycle is cyclo cycloaddition reaction. Now our next topic is assigning formal charges on intermediates and other ionic spaces, that is average electron theory. Definition of formal charge. Lewis structures frequently contain atoms that bear a positive or negative. If the molecules as a whole is electrically neutral, the sum of the positive charge must be equal to the sum of the negative charge. Thus, a formal charge may be defined as the positive and negative charges which must be assigned to the certain atoms within the molecules to be completely describe the Lewis structure. The formal charge on any atom within a molecule and hence on the ion and the intermediate as a whole can be easily calculated with the help of average electron theory. Average electron theory. According to this theory, the central atom is an equivalent molecule is surrounded by two types of electron pair, that is shared pair and lone pair. The shared pair are also called bonding electrons, while lone pairs are called non-bonding electrons. The average number of electrons on the central atom depend upon the number of bonding and non-bonding electrons around it. Whereas bonding electrons are divided equally between the bonded atom, and non-bonding electrons are assigned to the atom on which they reside. In other words, while calculating the number of average electrons on the central atom, half of the bonding electrons are added to the non-bonding electrons. So we can calculate the number of average electrons is equals to half of bonding electrons plus number of non-bonding electrons. If the number of average electrons thus calculated is less than that on the neutral atom, then the atom is assigned a positive formal charge equal in the magnitude to the difference between them. Conversely, if the number of average electrons on the central atom is more than that of the neutral atom, then the atom is assigned a negative formal charge equal in the magnitude to the difference between them. Once the formal charge on each atom of the molecule have been calculated, the arithmetic sum of all the formal charges gives the net charge on the ion as a whole. Formal charge on the atom is equal to number of valence electron minus number of valence electron. That is for the number of valence electron minus 1 by 2 of number of bonding electrons minus number of non-bonding electrons. If we represent covalent bond by lines or non-bonding electrons by dot, the above equation may be written as formal charge on an atom is equal to number of valence electron minus lines plus dots. Let us now apply the above theory to calculate formal charges on reactive intermediates such as carbocations, carbanions, free radicals, and the carbene. First is methyl carbocation. The incomplete Lewis structure of methyl carbocation is CH3. Formal charge on carbon, that is number of valence electron minus 1 by 2 into number of bonding electrons and number of non-bonding electrons. As we know that carbon has 4 valence electrons, that why we will write 4 minus 1 by 2 of non-bonding electrons are 6 and bonding electrons is 0, that we will get the plus 1. Thus the complete Lewis structure of the methyl carbocation is CH3. Similarly, we can calculate the methyl carbanion, methyl free radical, methylene, nitronium ion. Our next topic is methods of determining reaction mechanism. The mechanism of reaction implies the path which the reactant follows on their way to product. Since many chemical reactions proceed very rapidly, it is not possible to follow the reaction path directly. Hence, our knowledge about reaction intermediate is the mostly based upon indirect evidences. After characterizing the product, a number of mechanisms consistent with all the experimental observation are proposed. In most of the cases, new experiments are carried out to eliminate some of these mechanisms. If elimination leads to only one mechanism, then it is said to be a stabilized mechanism of the reaction. In general, the proposed mechanism for a reaction: first, it should be energetically favorable. Second, characteristics should account for all the experimental observation, and third is must be consistent with the mechanism of the analogous reaction. A number of methods are used to determine the mechanism of a reaction. These include product analysis, second is detection and isolation of the intermediates, third isotopic labeling, fourth isotope effects, fifth kinetic studies, and last one is stereochemical studies. All these methods are briefly discussed below. It may, however, be noted that it is not necessary to apply all the methods to determine the mechanism of a particular reaction. So let's start from the first. First is product analysis. The first step in investigating the mechanism of a reaction is the identification of the product and determining their relative amounts. To illustrate this point, let us consider the following reaction. First is the hydrolysis of two isomeric allyl chlorides, first and second, leads to a mixture of 85% of tertiary alcohols and 15% of primary alcohol in structure number 4. Since the composition of the products remains to be the same in either cases, therefore, the hydrolysis of these two compounds occurred through a common intermediate, that is the fifth. Second is the ketoaxims. On treatment with an acid, that is H2SO4, H3BO4, PCl5, SOCl2, etc., undergo Beckman reagent to give the corresponding substituted amides. Product analysis has revealed that during this rearrangement, it is always the group anti, or we can say trans, to the OH group which migrates and thus help the determine the mechanism of Beckman reagent. Third is crossover experiment. Crossover experiments are quite useful in determining whether a particular reaction in a one-step or two-step process. In these experiments, the same reaction is carried out with a mixture of two similar but non-identical reactants, and the product thus obtained are analyzed. To illustrate the role of crossover experiment in determining the mechanism of organic reaction, let us discuss Frey's rearrangement of esters, which involves migration of acyl or aryl group from the oxygen atom of the benzene. These two esters on treatment with anhydrous AlCl3 under similar condition undergo rearrangement at approximately at the same rates to give the products 8 and 9 respectively. If we treated 4 toluene benzene in the presence of anhydrous AlCl3, we will get 2 hydroxy 5 methyl benzophenone. Similarly, if we treat 2 chloro 4 methyl phenyl acetate in the presence of anhydrous AlCl3, we will get 2 hydroxy 3 chloro 5 methyl acetophenone. If the same reaction is now carried out with the mixture of these two esters 6 and 7 under similar condition, two possibilities arise. If the reaction occurs through coincidentally in the one step, the 4-tolubenzoate will always give the ketone 2 hydroxy 5 methyl benzophenone, while the ester give 2 chlorofoil 4 methyl phenyl acetate will always give the ketone 9. Next is detection and isolation of the intermediates. Many organic reactions occur through formation of intermediates which may either be stable or unstable. The stable intermediates are isolated and then characterized. The unstable intermediates, on the other hand, are either detected by spectroscopic methods or are isolated by tapping them with reactive substrates are discussed below. First is isolation. If the intermediates are stable, they are usually isolated by stopping the reaction before it is completed or by using relatively Miller condition. For example, three intermediates, N-bromomide, its anion, and its isocyanate have been isolated in the Hofmann bromide reagent of primary amides to primary amines on treatment with Br2QH. Thus, any proposed mechanism for this rearrangement must account for the formation of all these intermediates. Next is detection. Unstable intermediates are often detected by a spectroscopic method. For example, intermediacy of carbocation in intermediates in SN1 mechanism and ES reactions has been established by nuclear magnetic resonance means NMR spectroscopy. Similarly, carbocation intermediates such as in 12th its electrophilic substitution reactions have been characterized by their NMR and electron spectra. Free radical mechanisms can be detected by electron spin resonance ESR spectroscopy. C is trapping. Unstable intermediate can also be characterized by trapping. For this purpose, the reaction is carried out in the presence of compound with which it is known to react rapidly. First is carbene. Carbene formed during a photochemical decomposition of diazomethane can be trapped as cyclopropane derivative when the decomposition is carried out in the presence of cyclohexene. Second, benzene is formed during decomposition of benzene diazonium to carboxylate can be trapped by anthracene to form tryptophan. Third is carbocations are trapped by reacting them with nucleophiles. For example, the carbocation formed during the reaction of Br2 to ethylene can be trapped by a number of nucleophiles such as I negative, NO3 negative, H2, etc. Next is isotopic labeling. The mechanism of any reactions can be studied by using molecules in which atom is substituted by isotope. For example, first is hydrolysis of esters. The mechanism of hydrolysis of ester, whether it involves acyl oxygen or alkyl oxygen fusion, can be solved by hydrolyzing N-amyl acetate in H2 18O. Since the hydrolysis yields an unlabeled alcohol and a labeled acid, hydrolysis of ester involves acyl oxygen rather than alkyl oxygen fusion. Next is Cannizzaro reaction. Cannizzaro reaction involves transfer of a hydrogen from one molecule to the other. The question whether the hydrogen which gets transferred comes from water or the aldehyde can be solved by carrying out the reaction with deuterated benzaldehyde instead of benzaldehyde. Since the deuterium is exclusively located on the carbon atom of the benzyl alcohol carrying the hydroxyl group, the possibility of exchange of hydrogen with the hydrogen atom of the water is ruled out. Thus, there is the transfer of deuterium from the carbonyl group of one molecule to the other, and during this transfer, deuterium never gets detached. A possible mechanism considered with the above observation can be visualized. Further support to the above mechanism comes from the observation that when the reaction of the benzaldehyde was carried out in D2O, the recovered alcohol containing no alpha deuterium, indicating thereby that the hydrogens come from another molecule of aldehyde, not from the solvent. Our fourth type is isotope effects. While discussing isotopic labeling as a tool to investigate reaction mechanism, we have made an important assumption that there is no difference in a chemical behavior of different isotopes, and hence the chemical properties of the compounds are not quantitatively changed when a particular atom in a compound is replaced by isotopes. However, in actual practice, isotopes, because of the different masses, so affect the rate of the chemical reaction. The variation in the rate of a reaction when an atom in a compound is replaced by its isotope is called isotope effect. Usually, it is very small. However, if the replacement of an atom by an isotope is involved in the rate determining step of the reaction, the magnitude of the isotopic effect may be quite large and is called primary isotope effect. Since the mass of a deuterium atom is double and that of tritium atom is triple, and then atom is replaced by deuterium or tritium, is it is usually expressed in the ratio KHD by KD or KH by KT respectively. The value of this rate ratio is always greater than 1, which means that the compound containing hydrogen reacts faster than the compounds containing deuterium or tritium. Typical value for KH by KD and KH by KT are 7 and 16 respectively. The reason for the primary isotope effect is that the bond dissociation energy of CD bond is more than of CH bond and even greater for the CT bond. Therefore, the energy of activation for cleaving the CD bond would be much greater than that of a CH bond, and hence the rate of reaction involving CD bond cleavage will be slow. It may, however, be noted here that if the CD and CH bond cleavages are not involved in the rate determining step of the reaction, then the rate of the reaction will be hardly affected when hydrogen is replaced by its isotope. Deuterium or tritium. Most of the studies of isotope effect have been carried out using deuterium and not tritium because it is more easily available and also because tritium is radioactive. Primary isotope effect and reaction mechanism. Primary isotope effect is a powerful tool in determining the mechanism of many reactions. For example, A is the dehydrohalogenation of isopropyl bromide. The rate of dehydrohalogenation of isopropyl bromide with sodium ethoxide is considerably reduced when the hydrogen's atom of the methyl group are replaced by the deuterium. A large isotope effect definitely suggests that the rate determining step of a reaction involves the cleavage of the CH bond. As such, of the following mechanism for the above reaction is ruled out because in the mechanism CH bond is a fast step. B is nitration of benzene. Nitration of benzene is an electrophilic substitution reaction. Here, nitronium ion attacks the benzene ring, forming a carbocation intermediate which then loses a proton to give nitrobenzene. In case hexadeturated benzene or hexaiterated benzene is used in the place of benzene, the rate of the nitration has been found to be the same. This means that nitration of benzene does not show any isotope effect. In other words, the rate determining step of the reaction does not involve breaking of the CH or CD or CT bond. Conversely, attack of nitronium ion on the benzene ring is the rate determining step while the cleavage of CH bond is a fast step. Thus, the correct mechanism for nitration of benzene may be formulated as follows. Benzene, when benzene is reacted with nitronium and the first step is slow and then other is fast, then we will get the nitrobenzene. Fifth is our kinetic evidences. The kinetic evidences alone is not sufficient to determine the mechanism of a particular reaction. However, these studies give useful information about the rate determining step of the reaction. It is often possible to rule out many mechanisms simply on the basis of rate law. The most important example where kinetic studies have been useful in determining the mechanism of the reaction is the hydrolysis of alkyl halides. For example, the hydrolysis of methyl bromide shows second order reaction, that is minus d of CH3Br concentration divided by dt is equals to k of CH3Br into OH concentration. This rate law suggests that both CH3Br and OH negative ion are participating in the redetermining step of the reaction. Such reactions are called SN2 reaction and occur in a one step through the participation of a transition state. In contrast, the hydrolysis of torch butyl bromide show the first order kinetics. Says the rate law depend on the concentration of CH3 thrice CBr and is independent of the OH negative ions. Therefore, the rate determining step involves only CH3 triple CBr since reactions are called SN1 reaction and occur in two steps. The first step involves ionization of the alkyl halide to give a carbocation intermediate. This is the rate determining step of the reaction. In the second step, the carbocation intermediate is rapidly attacked by the nucleophile, giving the substitution method. Our last method is called stereochemical evidences. Sometimes the mechanism of the reaction can be determined by the following stereochemistry of the reactants and the product. For example, the mechanism of nucleophilic reaction, that is SN1 and SN2, have been investigated by carrying out reaction with optically active compounds and then checking the chemical purity of the compounds. First, a mechanism of SN2 reaction. Hydrolysis of optically active 1-chloro 1-phenylethane with aqueous KOH give racemic mixture of 1-phenyl ethanol. Racemization of the product suggests that the reaction occurred through a planar carbocation intermediate. Since the attack of the nucleophile, that is OH negative, ion on the carbocation can occur from both the faces, that is front and the rear, with almost equal ease, giving 50-50 mixture of two enantiomers. From the above discussion, we conclude that SN1 reaction occurs through a carbocation intermediate. Next is the mechanism of SN2 reaction. Hydrolysis of optically active 2-bromo-octane gives optically active 2-octanol. This can be explained if we assume that attack of OH negative ions occurs through the side opposite to the bromine atom, giving first a transition state which then expels the Br negative ion to the product. During this reaction, the conversion of configuration occurs. This is called the Walden inversion. From the above discussion, we conclude that SN2 reaction are one-step reaction in which optically active reactants give optically active compounds with inverted configuration. Last is elimination reaction. The dehydrohalogenation of cis-1,2-dichloroethene gives chloroacetylene 20 times faster than the corresponding trans isomer. This suggests that E2 reactions occur more rapidly when the departing group are in trans orientation than when they are cis. So then at last summary for the review. First point is called fish arrows are used to indicate one electron movement, whereas curved arrows are used to denote two electron movements, while double-headed arrows are used to separate various canonical structure. Second point is if a covalent bond breaks in such a way that each atom of the covalent bond takes away one electron of the shared pair. It is called homolytic fission. Homolytic fission produces free radical. It usually occurs in nonpolar solvents and is favored by high temperature or UV rays. Third point is if a covalent bond breaks in such a way that both the electrons of the covalent bond are taken by one of the bonded atom, the mode of the fission is called haplolytic fission. It usually occurs in polar solvent. Fourth point is called electrophiles. Electron-loving species are called electrophiles. These may be of neutral or positively charged species. The examples of neutral nucleophiles are carbene, RnBF3, AlCl3, FeCl3, etc. Positively charged nucleophiles examples are H positive, H3O positive, Cl positive, Br positive, R positive, nitronium, benzene, diazonium, etc. Nucleophiles. Nucleophiles, loving species are called nucleophiles. These may be neutral or negatively charged. Neutral species example NH2, H2O, RNH2, RHO, etc. Negatively charged species Cl negative, Bn negative, hydrides, cyanides, RO, etc. Organic reactions are of seven types. Reactions in which one atom or a group in an organic molecule is substituted by other atom or group are called substitution reaction. Thank you. That's all for the day.